Hey, everybody. Welcome back to the lecture. So today, change of scenery, right? So, I think all of you know what's happened in the other building, so no need to discuss this further, but that kind of also will have like a slight impact on the lecture itself, right? So, but we'll see what we can do about this. Anyway, so today we're going to talk about, or we're going to start today about saliency maps, right? So we've seen in the last lecture things like feature visualization, right? Where we basically try to identify what are the input images or the inputs that trigger the activation or like the average activation of like the whole layer or something like this, right? And this seems to be like super interesting and provides some general insight into what makes the network fire at different like stages and so on, right? But there's yeah, there are certain limitations. The same like also for network dissection, where this other idea is that we actually have more like human-like concepts, and we basically try to identify if like this human labeled concepts are present in the let's say image, for instance, in this case, right? And we do this by computing basically the intersection over unity curves, right? So far so good, but sometimes we're rather interested in the actual question, like what part of this input leads to the model output, right? So instead of basically doing this analysis of the hidden states or like the activation state and so on, we actually want to see what causes the downstream prediction, right? So, and in case of neural networks, like I mean, this is significantly more like or significantly different from what we've seen before in terms of like a feature attribution, right? So we did like this the permuted feature importance and so on. We saw this, but of course with a neural network where there are learned features, right? So there's like significantly more complexity in the entire system. Like doesn't mean that we cannot use these issues, but there are better approaches, right? So in particular, in this case, we want to look into images as inputs, right? And see if we can somehow visualize the insights there. And in this case, we talk about pixel attribution instead of feature attribution, right? So in terms of pixel attribution, what does this mean? So if we again take our like ambiguous case of like Veda, Yoda, whatever that might be, right? And we say like, okay, we have some certain like values for the pixels and we propagate them through the network, right? So we actually end up with something that we refer to as scores. So like if you have a classification problem, for instance, usually you have like a categorical distribution at the end, which consists like of different elements for each class, right? And before we go through the softmax, we have like these scores, which are usually something like you can think of them as the logits that we had from our logistic regression, right? So the log of the odds that basically would correspond to these score values, right? So basically we can use the softmax afterwards and then have this actual probabilities on which class is the most likely here, right? Does that make sense? So we have these scores and then there's something afterwards happening where we then have a loss, right? So for instance, a binary cross entropy loss or something like this. Like a binary cross entropy loss, which says like, okay, we actually classified it as, let's say, like as the good guy, but the ground truth that we're to look into means that it's a bad guy, right? So we kind of have to adapt the weights, and we do this through backpropagation, right? So I think this should be clear to everybody. So like, I hope all of you have had plenty of lectures on MPL, like MLPs and so on, right? And also know all of the backpropagation stuff. I don't want to go through this in this lecture, but generally something worth noting is that what we have here is the gradient of the loss with respect to the parameters, right? So the gradient, like the change that we observed with respect that we want to have with respect to the parameters. So in saliency maps, we like slightly want to ask basically the question, so how much does each pixel, so how much does each input here contribute to the actual output? So that is different from just like optimizing a loss, right? So let's go one step back and look back at our linear models, right? So like the things that we talked about yesterday early in the morning, right? So we have this linear predictor where like beta in this case determines which parts of X actually contribute to the output Y, right? So which is exactly the question that we try to answer, just now not based on a linear model, but based on on pixels and on images, right? So but the question is still, can we achieve something analog to this linear classification for complex domains such as images, right? Or in particular, we for now want to look at individual classes, right? So even if we cannot answer this in general, let's look at one particular class for now, right? So in this case, for instance, we have our class C, and class C is like the output or like the classification of class C is subject to FC with respect to I, right? I represents the image, but we actually can rewrite this slightly and say like, okay, if X represents a vectorized representation of this image, right? Then we basically can say, okay, we can approximate, the question becomes, can we approximate like FC of I as beta TX, right? So as a linear predictor over the vectorized image. Is that clear so far? Right? And if we are able to do so, then beta basically, again, same as in a linear model, gives us our attribution to the output, right? So that one basically tells us like, okay, each of those X contributes beta much to the output, right? That's the idea here. Okay. However, like the problem is that if we do this directly on the image itself or the pixel itself, that doesn't perform very well at all, right? So that's not a good idea to go this way. So we require something more complex. Usually what we do is in terms of images, like we use like convolutional neural networks, right? I mean, these days there's also a lot of work with like vision transformers, which like are a different approach, but like let's just stick to convolutional neural networks here for now, right? So the idea is that even though we cannot have the classifier directly, we can basically do a first order Taylor approximation of it, right? Which then basically would be a linear approximation of our overall classification problem. Does it make sense? So, okay. So I'm not going to go through Taylor expansions, but like if you don't know what it is, like just have a quick look up. There's more than enough material on for self-study here. But the idea in general is that we now basically have this derivative term here with like the insertion of x0, like the particular element that we're looking at. And this is what we usually refer to as our saliency. And if you look at this now, if you think about this as the saliency, right, like or as our beta terms, then this just becomes a line. Does it make sense? Right, so Sx is basically the equivalent to beta here. Right? Okay. So with this, what does this mean? So if we now go back to our like previous neural network representation, right? So where here we had basically our loss that we backpropagated through, instead of actually computing the derivative of the loss with respect to beta, we basically compute the derivative of the score, like for one particular class, with respect to the input parameters, right? So it's a different type of gradient that we're computing. So when we talk about gradient-based methods in this case, right, like saliencies and so on, we don't refer to the gradient of the loss, right, but to the gradient of the scores with respect to the input, right? That's important. Okay. So with this now, if we actually have our saliency, right, so we can like choose different ways of visualizing it, right? So we can only visualize the absolute, or like we can visualize the absolute, or only the positive or negative examples, right? So this is up to us. But computing the saliency allows us then, for instance, no matter what we do, like I hope it's visible enough, to basically have like this idea, okay, like given the scores for one particular class, which pixels contributed to that score, right? So if I have like a very high score for like, let's say, for instance, frog on the way to the right here, so which pixels like helped in having the high score for the frog, right? So then we can see basically like this little heat map over here. It's like, okay, these pixels seem to have contributed, these ones over here and so on, right? So this like provides us some interpretation, right? Any questions so far? Okay. So the issue with, or like one issue that occurs with saliency maps is like that when we compute the saliency map, like we also have to propagate through the activation functions, right? And the very common activation functions these days are ReLUs, right? I mean, honestly, these days, like the most modern approaches don't use ReLUs anymore, right? They use like JLUs and CELUs and like self-regularizing activation units. But still, I think ReLUs had a big impact, and to this day are still used widely, right? In particular, in actually more like product-oriented models and not in research. But in research, we actually, I think, moved on to a big degree. But in case you're not familiar with what a ReLU looks like, it's basically like this ramp function here, where everything positive is just like a linear mapping of the inputs, right? And everything negative is cropped at 0, right? Does this make sense? So that's what a ReLU looks like. So what's the problem with this type of activation? Mhm.
Vanishing gradient.
Vanishing gradients, right? But okay, so can you elaborate on that? What that means?
So, like, if we propagate through the models, some weights tend to grow exponentially, or
But that's not vanishing. That's exploding.
Or they decrease, reduce exponentially, and get lower, almost zero.
And why would, okay, so where would the vanishing happening here?
For small gradients under zero. Oh, I think I'm lost. I think I meant dead neurons, not vanishing gradients.
Mm. Yeah, you also raised your hand?
Yeah, the problem with the normal reading function is that below a value, the input value of 0 is constant.
Yeah. So basically, so this actually goes together, right? Like, so with the zombie neurons, the issue is that everything, like every information that is smaller than 0, right? Like, but this is still valuable information, gets lost. So we don't actually know like how much in the negative we are, right? And in particular, like with respect to the inputs, like if we compute the gradients with the inputs, that's in particular a big issue, right? So because like there might be actually significant information that tells us something about the pixels down the line, right? But we basically chop this off so we don't have this info anymore, right? Does it make sense? So that's like a particular issue here. So what can we do about this? So the first idea here was that we only propagate back the gradients where the activation of the previous layer was not 0, right? So we again have like a Kronecker delta or indicator function that basically says like, okay, if the layer before had like 0 values here, we're not propagating those arrows back, right? And we keep the arrows that we had there to begin with. And this was the original Salem map formulation in 2013. And then almost like, oh yeah, and or vanilla gradient method. And almost immediately, like there was a response or like a co-development actually, where they solved the same issue in a slightly different way, where they said like, okay, if the current layer actually has non-zero values, right? That's when we propagate it back. So the difference is basically the previous layer or the current layer, right? And those two look very similar and are, but there's like slight differences between those two approaches, right? So if we now just look at it illustrated, so this is taken from the lecture from Protopapas in 2021, right? But so basically this illustrates kind of the issue, right? So the solution. When the Salem maps approach from 2013, the idea is that we actually see our activation map, and everywhere where there's a 0, right, we don't basically like take the information back, and only where there's a non-zero information, we take the information with us, right? When we back propagate. And in this approach here, we do the other, like we basically go and look into the current step, right? So where we do something very similar, but slightly different. And that has different implications in terms of like stability of the method and so on and predictions, right? But they're like honestly, from just empirically, the solutions, they will still be very much in this domain, right? So we will still have like this level of explanation. So it doesn't change that much, right? Yeah. By the way, who thinks that these are very good explanations? So what's wrong with these explanations if you don't like them?
Heavily focus on individual pixels and not broader regions.
But that's what we want. We want pixel distribution, right? But you say like pixel distribution in general is a bad idea?
I think single pixels might not be as relevant when they don't have like the intrinsic contact.
Mm-hmm. Okay, like there was another sense. Like I don't disagree. Like,
Okay.
like it's
basically it's hard to interpret,
Mm-hmm.
Which might be just the case for the model in this case,
Mm-hmm.
but also they are very unstable, which is also
Mm-hmm.
not good.
Other thoughts?
Perhaps some filtering of maps would help. For example, now these maps kind of look like noise patterns that
Mm-hmm.
noise. So what you could do is only show values that are above a certain threshold.
Yeah.
More than values around it.
Mm-hmm. Fair. Like, yeah, you can threshold them basically, right? Like you can basically say like, okay, we chop everything off. And like in practice, you would also like, kind of do this before you overlay it onto the main image, right? There's something like, unfortunately, this year we will not talk about this, but there's something that might still be. I'm not sure to mention it now. Or I might talk about this early, but still, how I think. Or I guess a lot of you, if not all of you, have heard about adversarial attacks, right? So who can tell me in their words what an adversarial attack would be?
It's basically a perturbation of the input image that looks not like very, very similar to the original image that significantly changes the prediction of the model.
Mm-hmm. Exactly. And so the problem is that we can do this here too, right? So like with these pixel distributions, you can basically manipulate both like the data or the network, right? Or both together at the same time. So like you can do poison well or like an actual like model attack. But the issue with this is that we can trigger or cause like a highlighting of something completely irrelevant, right? And still maintain the correct performance, right? So it seems, and that's like an indication for two things, right? For one, that these things can be like misused, right? These tendency maps, because you can basically say like, oh, the model highlights X and Y and so on, and it seems to be correct, but down the line it actually uses something evil to do the classification, right? But the second thing is also if we can easily manipulate the activation of individual pixels without destroying the score at the end, right? Or without like affecting significantly classification, that kind of indicates that those things are meaningless, right? Does it make sense? So there's like a little bit significant issue. And last year we had an amazing talk, like check the videos if you want, by Christian Wresneger, who's a professor here at KIT, who actually investigates also like this adversarial attacks and so on. He's like an expert in security and like some really cool stuff there, right? So unfortunately this year we will not have the lecture. Yeah, coming back to the topic. Okay, so instead of pixel distribution, what we can also do, right? So again, so there's the issue and so on. But what we can also do instead is, or like what might be more interested, and like the suggestion came earlier, that instead of looking at individual pixels, what if we actually care more about like an entire area, right? So if we want to highlight, okay, this is basically what the overall classification focused on, right? And that gives us the approaches of class activation mapping, or CAM short, right? That we will talk about in the next couple of minutes, right? Yeah, proposed by Zhu et al. In 2016, right? So the idea is that, like, again, I already gave you an outline of what an MLP like this, or like what a network like this usually looks like, right? So we have the convnets, we have the scores, we have then the softmax layer, right? And then we have the classification, like the classification loss or whatever we're going to use, right? So in this case, what we do here, we take the network as it was trained already, right? And chop off the MLP and instead do like global average pooling. So like, who knows what global average pooling is? Okay, so global average pooling, really, really simple. In this case, if we have like multiple channels, right? For each channel, we average over the entire other dimensions, right? So if we have n channels that are b times w wide and large, right? We end up with 1 by 1 by n, like outputs, right? So we take the global average per channel. That's all it is, right? And then we basically have, like, this will be the dots over here, and then we have the weighting, like, of all of these global channels, these global poolings, combined into the classification itself, right? And we try to maintain the classification, so we actually have a retraining step. So we train this part again, right? And then try to basically learn the correct weights for the global average pooling to identify or to maintain the classification, right? Does it make sense? So, and if we like maintain the classification, so we kind of hope that like through these values, they basically become the scaling or the weighting of the different channels. And the different channels give us kind of like an insight what was actually active at a point in time, right? Like what was like the important weighting terms. And by combining this gives us our overall classification class activation map. Does make sense? Okay. So who did I lose? Like, who's still with me on this one? Just a few people. Like, who's with me? Okay. So half. It's not a good rate. Like, so for those that are not with me anymore, where did I lose you? Again, we're talking now about like this idea, right? That we want to have like entire like areas that we want to identify, right? And here the idea is that instead of doing this score base or like the score prediction through the MLP and then the softmax on top of it, we directly do pooling of the convolutional layers, of the last convolutional layers, like an average pooling, right? So, and then basically weight those outputs directly into the classification value, right? So that's clear. Okay. And then now that we have those weightings, we can actually take our conv maps, like the last layers, and just weight them with this and aggregate them. And the idea is that hopefully this way, right, we see how much each of those contributes to the individual class, right? So because for the first class, maybe the channel 2 and 3 are important, right? And all the other channels are not. For the second class, maybe 5 and 6 are important. And then the idea is that maybe 5 and 6 together constitute the head of a dog or something like this, right? And 1 and 2 together, the tail or something like that, right? And finally, like we basically just like upsample the last layer, the same as we did in the dissection, the network dissection part, and then do this overlay on top of the dog and then have them like all beautiful activation maps. And empirically looks that like it works fine, right? So we have like for instance identification of brushing teeth, right? But also similar, like for instance for cutting trees, which I personally found very interesting. You have obviously like not obviously, but it's really cool to see that we have the cutting part, right, of the trees, which is great. But at the same time, we also have the head of whoever does the cutting. So apparently, trees don't cut themselves, right? So you need to have like a person there too. Otherwise, it wouldn't be classified as cutting trees, right? What would be interesting, which unfortunately they didn't do, is to figure out what it would be classified if the person wouldn't be there, right? So would it be like dead tree or like cut tree, like in terms of like passive that it happened already, or like yeah, or if the person indicates that it's a current action that's happening. So these kind of insights would be super interesting, right? Also for explanation. Yeah. So now the question is like, since we're basically on like or like before we move on, any questions so far? Okay. So now the question is like, since we're like moving actually through like, or we're using like a gradient-based method here, right? Or we're optimizing our network usually on a gradient-based method, can we leverage those gradients, similar as we did in the pixel attribution, with CAM together? And that gives us GradCAM, right? Like, which is basically this combination of CAM and gradient-based methods, right? So this is like a multi-step process. I originally wanted to do like an image on the blackboard. Let's see if we can improvise that somehow. But the idea is, let's go step by step, right? We pass the input through the convolutional neural networks, and then we obtain the raw score at the very end. So before we do the softmax of it, like, right? So the log it, we take that one, and for one particular class of interest, right? Same again as for the pixel attribution, we're looking only at class C, right? And set all other activations to 0, right? So we basically only have this one and set everything else to 0. And then we backpropagate that gradient all the way until the last convolution layer, like last meaning not the one at the very beginning, but the one before the MLP, right? Before we basically or the last layer in terms of like after the convolution and the forward pass, right? That's important here. And then we weight each feature basically by that gradient, like each feature map by the gradients that we get there. Remember now, those are manipulated gradients because we set certain activations to 0, right? So those are different gradients. And the idea is by setting those to 0, like that the gradient now contains only information that was relevant for the activation of that particular class, right? And then we take this basically as kind of like a weight, right, for the feature map. Feature map here again being basically like our globally pooled last CNN channels, right? And then we basically just average over this, take our ReLU function, and then we can overlay this with our image, right? So for visualization purposes only, right? So it doesn't really like help us anything else. So are these steps clear enough, or should we do like an image or something like this on because I wouldn't know where to do it now. I don't think the university would like me to draw on this thing, and we never tried that one before, so we don't know how this works. We could try, but I'm not sure if it will be that great visible, like that well visible, and there are no pens. Obviously.
The other rooms, they have.
Yeah. Maybe what we're gonna do is we're gonna move on right now, and then I'll maybe provide like the image either afterwards. I'll do it like on a slide and send it to you guys, or like maybe in the break or something like this. I'll figure out what it pens because I don't want to like stretch this too long. Yeah. So, but yeah, if we look at GradCam, there's like a lot of different different methods that we're not going to go in detail that we can leverage here, right? So that like try to like make this more informative and so on, right? So like for instance, like a guided GradCam, right, or like a smooth grad also. But like one of the most we don't actually have GradCam ++ here. Okay, that's something that we need to fix. So GradCam ++ is basically the like at least to the best of my knowledge, one of the most current approaches. But overall, we can actually see like the different cam approaches, and GradCam itself actually seems to be quite nice, right? Is there anything wrong with the GradCam images? Do you have anything to complain about here? So first of all, like which one is your favorite, right? Like which one do you think provides the best like visualizations or the best explanations? Let's go step by step. So who's in favor of saliencies? Okay. Gradient input. GBP? Interesting, what?
I think because you can see the edges of the object you're interested in.
Sorry, what?
The edges.
Oh, the edges. Okay. So basically like the silhouette kind of thing here, right? Okay. Yes. Interesting. IG? Okay. Smooth grad? Oh, a lot of smooth grads. What makes smooth grads so interesting? So any of you, why do you like this most?
It strongly focuses only on the object of interest and not much of surroundings.
Mm-hmm. But don't you think the surroundings might be relevant? So for instance, if let's say if I know that this bird only occurs in Latin America and that this tree, but there's a very similar bird who also lives in Europe, but this tree is something that only occurs in Latin America, right? Like, and then I know because the combination that this is rather bird A than bird B, right?
Yeah, but then you might struggle with out of distribution. But yeah.
Yeah, sure, but like we have another what's it? No, you don't. That's almost the same. Okay. What about this one? Okay, so who likes this one most? Okay, why? Anyone?
I think it highlights the surroundings as well as the object of interest.
Mm-hmm. So what is like what's potentially the problem here with this one? Is there anything that you see that is?
So for example, the topics are made to be that in terms of role because it highlights a lot and also a lot of the I think it's a sea creature. I can't exactly make it out from here, but most of the ground is highlighted, but it's just repeating texture shows, so and it's not very clear what it shows. So I think possibly combination of the GradCam and the smooth grad would give the most information since it highlights both the outlines of the object. So it segments the space into two areas, as well as with the smooth grad the actual main focus of the model.
Yeah, I think that's a very fair critique. Like I think I would basically like stick to it too. I think you need to grab a chair. There are chairs like in the neighboring rooms, just cannibalize them. Okay, yeah, no. So I will tell you like the actual problem of this thing on the next slide, right? But towards the end, because this is basically what we're going to finish with. So yeah, the advantages of saliency maps, right? The explanations are visual and like we get quick, like we are very quick to recognize like the images or like the association there, right? It's faster to compute than model agnostic methods, like for instance, than SHAP or something like this. And there's like, as we've seen in the previous slide, there's many methods that like we can choose from that can like extend on and so on, right? So the disadvantage is it's difficult to know whether an explanation is actually correct, right? So because we only have like this qualitative, not the quantitative evaluation. The pixel attributions can be very fragile, as I mentioned, with the adversarial attacks and these kind of things, right? And the methods can also be like quite unreliable. But the biggest issue is that potentially there's some recent work out there, right, that indicates that these models, like particular GradCam, is insensitive to model and data. So why is this on the disadvantage side? So first of all, what does that mean, insensitive to model and data?
It's similar. It has a similar output if the model or the data changes.
Yeah. So basically, like if I have a different model, right, or if I have different, like, so I trained the same architecture and everything, right, but like somehow I have different performance, right? Like it seems to be insensitive to that, right? And in terms of data, like even if I trained it only ever on birds and I show it now frogs, it still like shows similar like or analogous results. So what does that indicate, if that is the case?
It doesn't really make it on the wall top.
Exactly. So what it means is it's basically an edge detector. So it learns something, or it indicates, it shows something that is universal, right, across like model performance and like it's also and all across data. So it is something very basic, right? So and like again, so the jury is still out on that one, but there is like some like critique research now on this one saying like, okay, that thing is not really like explainability or it's not explaining anything. It's basically just identifying edges. And if we now go back to the image, it's kind of what it looks like also, right? So it's a little bit like of a problem there. Okay, so with this, we're done with the saliency part. So it's now time for our 5 and 5. Go.